Hello. Congratulations on your midterm exam. Almost student did a great job on midterm exam. Today we are moving to chapter 4, equilibrium method. We already mentioned about this method, and in chapter 4 we are going to talk in deeply about this technique in plastic analysis and design. First of all, we are going to see some concept, something introduction. Okay. In the previous chapter, the basic assumptions and theorems used in the plastic analysis and design were already introduced. In this chapter, we will present a technique for plastic analysis and design. It is equilibrium method, or EM, equilibrium method. It's based on the lower bound theorem. As you already know, in plastic analysis and design, three conditions should be satisfied. The first condition is equilibrium. The second is mechanism condition. And the last one is plastic moment condition. Moment should be smaller than mp, plastic moment of the section. In equilibrium method, as you know, the relationship between strength of the structure and the applied load is found by adjusting the unknown redundance. It is for indeterminate structure, right? Indeterminate structure. So because of that, the equilibrium condition is always satisfied. Okay, the equilibrium condition is always satisfied because we develop relationship between strength and applied load. The second is the moment condition is not violated. Okay, violated. Moment condition is not violated. So because of that, then we call lower bound solution. Okay, the moment condition is always okay. It's no problem with m is always smaller than mp. Mechanism condition may or may not be satisfied. Okay, the mechanism condition may or may not satisfy depending on our assumption, initial assumption. Okay. Beyond that, we will have a procedure which can be used for analysis of structure using equilibrium method. It is general procedure. The first step is we assume a set of redundant moments. So try to check the best set. Okay, try to check the best set. So this step we assume a set of redundant moment. It corresponding to the plastic failure mechanism. If we assume the correct mechanism with correct set of redundant moment, then the result the solution is correct. This is easy for a simple structure, but not easy for a complex structure like a building frame, something. We are going to talk. We will talk later. The second step is to find the relationship between strength, maybe the moment, and apply load using equilibrium condition, or in another word is moment condition. So based on this redundant moment, the set of redundant moment, and we have applied load, and this step we develop the relationship between strength and apply load using equilibrium condition. And the last step. Okay, so in this step, using the equilibrium, we can solve the equation and find the unknown. The unknown here is moment. Okay, unknown here is moment. And the third step and the last step is mechanism check. We have to check the mechanism based on our assumption. If it is violated, then it is not correct solution, but it is lower bound solution. Okay, if the condition, the mechanism is not mechanism, then the solution is lower bound solution. But if the mechanism is satisfied, then the solution is exact solution. Okay, so we have three steps for equilibrium method in plastic analysis. The contents of this chapter, the first one is examine the lower bound theorem that form the basis of the equilibrium method. The second is to discuss the step involved in. The third content is to demonstrate the use of the equilibrium method for analysis and design of the simple beams or rectangular photo frames and gimbal frames. And the fourth content is to present the practical procedure of the equilibrium method for analysis and design of the large structure. That is the content of this chapter 4. Now I'm going to give you an example to illustrate the concept, the procedure that I just mentioned in the previous slide. Consider a bolt fixed end beam under distributed load, as you can see here. Okay, fixed end beam with distributed load. Okay, so take a look at this structure. How many redundants? In this structure? We have two redundants. Okay, two redundant moment here and moment here. So the beam has two redundants here and here. Second question is how many plastic hinges is needed for collapse mechanism? how many plastic hinge is needed for plastic hinge mechanism? 3, right? One here, maybe on here, and maybe one in the middle. So we need at least 3 plastic hinge for mechanism. Three plastic hinge is needed for mechanism. Okay, so because of two redundance, so we assume, no, not assume, but this is two redundant. M1 here and M1 here. They are redundant. And replace this boundary condition by redundant. Then we have similar structure with a simple beam and redundant. Okay, so this beam now become a simple beam with redundant. Okay, we can replace this beam by simple beam and redundant. And now for simple beam with applied load, okay, moment by applied load for the simple beam. Okay, then we have moment diagram. Moment here is 0 because of simple boundary condition, and moment here is WL square over 8. You already know. And moment diagram by redundant M1 and M1. This one is plus and this one is minus. Okay, by redundant moment. Then superimpose moment. This one plus this diagram plus this one equal to this moment diagram. Then here we have the maximum here equal to WL square over 8 minus M1, and moment here is M1. Okay, so here is the moment diagram of whole structure using superimposed moment method. Okay, so for plastic analysis and design, we have, because we need 3 elastic hinge for mechanism, then moment M1 here should be equal to MP, and moment, the maximum moment at the middle of the beam should be equal to MP too. Okay, so this one equal to MP and this one equal to MP. So by solving this equation, we have load, the limited load, okay, plastic limit load equal to 16 MP over L square. This is solution of these problems. Okay, and now we have here MP and here MP, because we assume MP and MP here. Then mechanism check, mechanism here, and mechanism. Then it is correct or exact. It is mechanism, right? Then it is exact plastic limit load. Because this problem is simple, so we know easily, we very simple to assume here is MP and here is MP, MP here and MP here, and we easy to check mechanism because it's simple. But in a complex structure, sometimes we don't know, or it's not easy to assume the correct mechanism. So that's why we have to do the moment check, to do the mechanism check to ensure if it is correct solution or not. If it is not solution, then it is a lower bound solution. Now we move to another. Now we assume m1 equal to 0. Okay, now we can assume, okay, m equal to 0, m1 the redundant equal to 0. And what happened? That is wrong, we know, but we just assume m1 equal to 0. Then here is MP. Here is MP, right? And now this one equal to WL square over 8 and M1 equal to 0. Then we have the load equal to 8 MP over L. The correct one is 16 MP and over L square. But it is wrong. So how to say? For analysis, it is two-step, right? For analysis, it is two-step. So that's why we call it is lower bound solution. A lower bound solution. Okay, so we use three steps, 1, 2, and 3, to analyze this structure. And now we understand the procedure and the concept of the equilibrium method used in plastic analysis. Okay, we are going to continue this to apply this method in some more example in plastic in analysis problems or in design problems. Okay, we will talk later. Second problems that we are going to talk about today is lateral torsion buckling. Lateral torsion buckling. What is lateral torsion buckling? Let's consider a beam. As you can see here, this is top view. Okay, top view of the beam, and it is side view of the beam. Okay, can you imagine this beam? It is side view. So let's say this beam has I section. This is compression zone, and this it is tension. Okay, tension here and compression here, maybe. And under the load, it is bend. Okay, but sometimes it is a lateral deflection of the compression flank. Okay, because this flank is under compression. So under compression mean under not compression condition. Sometimes it make the structure to be bucked. Okay, so that's why this beam sometimes deflect in the horizontal, not vertical but horizontal direction. Okay, so this is called lateral torsion buckling. Okay, lateral torsion buckling. The beam is rotate. Okay, here this section is rotate. Not only more deflection, vertical deflection, but also horizontal deflection. Then combination between the vertical and horizontal deflection. It is rotation. It is rotate. Okay, it is rotate. Then this phenomenon is called lateral torsion buckling. Okay, lateral torsion buckling. And now you understand the concept of lateral torsion buckling due to the compression of the upper flank under bending. Okay, so we have to consider this phenomenon in our analysis and design of structure. Why lateral torsion buckling? Lateral torsion buckling occurs due to the high unbraced slenderness ratio of the narrow beam. Okay, because of the high unbraced slenderness ratio of a narrow beam. What is the effect of lateral torsion buckling? What is its effect? The lateral torsion buckling may prevent the beam from attaining its fully plastic moment. In other words, the lateral torsion buckling prevent the beam cannot achieve the fully plastic moment. That is problem. And how to ensure the proper moment and rotation capacity to achieve the fully plastic moment. Okay, how? This figure shows the relationship between the moment capacity and unbraced length. LB is unbraced length. Unbraced length means the length between the two connections of the beam, for example, from here to here. And if we have a horizontal beam here, it is braced. Then the length from here to here is called unbraced length. Okay, unbraced length. For example, like that. And this is relationship between moment capacity and unbraced length. If the length is too big, let's say the length is greater than LR, then it is elastic buckling. If the unbraced length is between LB and LR, then it is elastic buckling. If the length is smaller than LP, then plastic moment. But in plastic analysis and design, we should assume it is need to meet the requirement of L smaller than LPD. Okay, LPD for plastic design. Okay, so it also satisfy moment capacity and rotation capacity. So LP here, this point, equal to this equation. If the length is smaller than this value, then MP, but MP is achieved, but not rotation capacity. Okay, so but if L smaller than LPD, using this equation, LPD using this equation, okay, then the plastic moment and rotation capacity both are achieved. Then, in another word, in plastic analysis and design, we should the unbraced length should be smaller than LPD. Okay, smaller than LPD. If not, we need a lateral brace like this. Okay, it is by floor concrete floor slab, or by using the lateral brace to develop full moment. Okay, So in analysis, you have to check, okay, analysis and design, plastic analysis and design. You have to check unbraced length should be smaller than L PD using this equation. If not, you have to add the lateral brace. Okay.